I'll ask a really naive question, which is that like throughout this talk, something that I don't know if I found it reassuring or worrying, but like you seem as well like quite surprised that sometimes this two categorical stuff is enough, you know, that somehow like things work. And this is something I've never really understood. I'm one of these people who is much more comfortable with the number infinity than the number two. Like two categories really scare me. So like, is there some, I don't know, like, is there some good moral justification for like, why don't you need to do three categories? Like, why is two somehow enough? You know, I know this is a very big, vague question, but hoping you can say something to, I don't know, reassure me.
So I'd have to say that maybe, so Emily points out in the chat that in the cartoon that I drew of us, the last frame of it is that she's drunk her coffee and I still have, famously, when we drink coffee together, she always drinks her coffee early and I leave mine until it goes cold. And it was probably in one of those discussions that we were both surprised by the fact that somehow this quotient, like interpreting things like adjunctions in this quotient, was at all an interesting or useful thing to do. So, I mean, to us originally, I think it was quite a surprise. I think, I mean, of course, at least some of this is not deep philosophy. It's looking in specific models and asking the question, what actually, when we look at these structures in here, what actually happens? Fundamentally, what it comes down to is that it turns out that things that can be characterized by universal properties can probably be expressed in the homotopy two category context, because there's enough information being stored there to give us, for instance, the theorem that says from an equationally defined adjunction, I do get all of the higher homotopical universal properties that I need. Things that require, however, equational data, that's not going to work there. So this is the reason why it works for adjunctions, but it doesn't work for monads. So if you take a monad in the homotopy 2 category, that is not the same thing as a homotopy coherent monad. It's not the right notion. The reason that we can go backwards and forwards between those things, well, the reason that this is at all useful is that starting with an adjunction, it has the right universal property, the infinity categorical universal property. And using that universal property, I can then build up for that adjunction all of the higher coherence data. And this is sort of common in, even if we look at adjunctions or bi-adjunctions between bi-categories, the relationship, the existence of the unit and co-unit and the triangle identities are enough to characterize the universal property. But we know that when we start using that universal property, we then have higher coherences. So we have this swallowtail axiom that comes out there. So again, the reason we can rebuild that from an adjunction is because that's built from the universal property for which the first two layers were enough to specify. So, I mean, certainly my philosophy on this is if it's a universal property, I can express it in the homotopy 2 category. If it's something equational, then I'm going to have to prove a homotopy coherence result. The other thing I should say is that a lot of this, certainly in my mind, is modeled on, at the next dimension down, on derivator theory, where again, there are certain things we can do in the homotopy category, but so a bunch of things that we can express in the homotopy category of a model category. But to get the full theory, we need to do something a bit more. So sometimes we need to prove a coherence result in derivator theory. So, I mean, one way of thinking about this, probably not for most people in the audience, is that really what we're looking at is some fragment of 2 derivator theory here. And so in the same way that derivator theory suffices to tell us about universal properties, that's really what's going on here. But again, in derivator theory, if we've got something that's equationally defined, I've got to sit down and do a homotopy coherence proof about it. Yeah.
That's a nice, like, good, like yardstick or whatever to have, this idea that like universal properties means it's probably going to pass through in this thing.
Yeah.
Okay, thanks. That was helpful. Thank you.
But that doesn't kind of make a difference between true and infinity, does it? I mean, because, what is kind of bothering me with this explanation is the fact that monads have equalities. I mean, you define them through equalities on the triangles, but the adjunctions do the same. So why such a big difference?
So I guess so there's a bit of a trick going on in this, which is that although the equationally defined adjunction is an equationally defined structure in a 2 category, that I can test information inside that by looking at maps out of other things in that 2 category into it. And those other things allow me to express arbitrarily complex shapes inside the categories on either side. And that's what allows me to show that an appropriate universal property holds for these. Unfortunately, that technique doesn't work for something like a monad, essentially because the monad isn't defined as a universal construction. So it's sort of, I guess the status of equationally defined adjunctions. Again, maybe the remarkable fact is that adjunctions can be defined both universally and equationally. And maybe we shouldn't be expecting that. It just happened. Uh-huh. We got told that early enough in our categorical education that we just accept that. But maybe that's something that we should be a little bit more suspicious about. Maybe that's something I should have been more suspicious about when Pino Rossellini taught me about adjunctions when I was a child.
Okay, so briefly, thank you for this beautiful talk. It's been most illuminating for me after listening to a lot of related talks. My question is this: I come currently, from my interest in category theory, from the point of view of what I might call the semantics of biological processes. How control signals are developed in the context of biology, and how the control of control evolves. Everything about biology is all about the evolution of higher and higher levels of control. And so I look at, infinity categories as kind of my, how should we say, hopeful arc on which to float into this biological domain. My question is, do you and your fellow wonderful Australian categorists have interest in applying this theory in that context in which we're trying to model basically the higher order semantics of biological processes, if that term makes any sense to you?
Mm-hmm. I obviously can't speak for my colleagues, although, I should say that one should always admit one's faults. And maybe one of our faults here in Australian category theory is we are terribly abstract.
That's good.
And we tend to concentrate on the abstract rather than the application. Certainly that is something that we're interested in. Also, certainly I personally am interested in. But as yet, I don't really have any particular handle on how to get it to work in the infinity categorical context. It's not. I know that I guess sort of work that I have pondered categorically in the past with maybe stuff that Robin Milner did on some of these questions, and sort of his categorical presentation there. It does seem to me that there are some aspects of that could be put into this kind of a framework, but I don't have I'd love to have more of a chat with you sometime offline about that, because it's certainly something I'm very interested in, but really don't know a huge amount about.
Thank you.